Welcome to this explainer. Today we're going to do something really cool. We're taking abstract, highly complex machine learning algorithms and translating them into clear, beautiful visual geometry. We're literally going to see how raw, messy data can take on a physical shape. Okay, let's dive into this.
Here's our roadmap for today. We'll start with the business of grouping data, then explore the geometry of distance, break down the k-means algorithm, evaluate our cluster quality, and finally, visualize it all with t-SNE.
Part 1. The business of grouping data. Finding hidden structures in the noise.
To anchor all this math to the real world, imagine you run a retail company. You've got thousands of customers, and you want to segment them based on their income and how much they spend on wine. Now picture a giant scatter plot of all this data. Every single dot is a person, but there are no labels. We don't have predefined tags like high-value customer or budget shopper just handed to us. So the big question is, how do we mathematically discover these segments? How do we group things without knowing what the groups even are?
Well, this brings us to a really fundamental distinction in machine learning. In supervised learning, the labels are already there. You're basically training the machine to recognize something it already has the answer key for. But clustering? That's a form of unsupervised learning. No target labels are provided at all. The algorithm has to visually and mathematically discover the structure all on its own. And it does this based on one core rule. Points inside a cluster should be similar, and points in different clusters should be dissimilar.
Which leads us to part 2, the geometry of distance, measuring the space between data points.
You see, to a machine learning algorithm, similarity isn't some vague abstract concept. It's quite literally just measuring physical space. If points are close together in our visual geometry, they're similar. If they're far apart, they're dissimilar. Take Manhattan distance, for example, which is also known as city block distance. Mathematically, sure, it's the sum of absolute differences across dimensions. But visually? Paint a picture in your mind of navigating a grid in New York City. You can't just walk diagonally through a massive skyscraper, right? You're forced to move horizontally down the avenue and then vertically up the street. That's exactly how this metric calculates space, by strictly following the grid lines.
But what if there were no buildings in the way? What if you had a bird's-eye view and could just fly directly from point A to point B? Well, that is Euclidean distance. It's the straight-line distance between 2 points, calculated using good old Pythagorean theorem, taking the square root of the sum of square differences. This direct, visual path is what we typically rely on for our main clustering algorithms.
But hold on, because there's a massive visual trap here. Let's look back at our retail data. A customer's income could easily be $80,000, while their wine spending might be, say, $250. If we just calculate the distance on these raw numbers, a $20,000 difference in income is going to completely obliterate a $100 difference in wine spending. It totally distorts our geometry. To fix this, we use something called z-score standardization. We subtract the mean and divide by the standard deviation. Basically, this forces every single feature onto an equal visual playing field, ensuring no single variable warps the actual shape of our data.
Part 3. The k-means algorithm. Animating the clustering process. All right, with our space measured and scaled, we assume there's a set number of groups. We call that k, and we need to find a representative center for each. Imagine our data is just a massive cloud of gray dots. Step 1, we randomly drop k number of colored center points, called centroids, right into that cloud. Step 2, every single gray dot calculates its Euclidean distance to these new centers. Step 3, the dots magically change color based on which centroid is closest to them. Step 4, the centroids then move to the physical center, the mean, of all the dots that share their color. And step 5, we repeat. Just visualize those colored dots shifting, recalculating, and shifting again until they finally lock into completely stable, fixed positions.
Now, I should mention, throwing our starting points in completely at random can actually be a disaster. Think about it, if all our centroids accidentally land in one super dense corner, our final shapes are going to be completely skewed. So we use something called k-means plus initialization. We pick one point, and then deliberately choose the next point to be as far away from that first one as visually possible. We absolutely need our starting anchors to be spread out across the entire dataset if we want a beautiful, accurate cluster.
Part 4. Evaluating cluster quality. Measuring the sharpness of our shapes.
Since k-means forces us to choose the number of clusters, our k, right up front, you're probably wondering, how do we actually know we picked the right number? Well, we want our clusters to be tight and dense. We measure this using the within cluster sum of squares, or WCSS. which basically calculates how close every point is to its centroid. If we plot this compactness on a graph against different values of k, the curve will slope downward. What we're visually looking for is the sharp elbow on that graph, the exact point where adding more clusters stops dramatically improving the tightness. That bend, that's usually our optimal k.
We also use the silhouette score. This measures both how tight a cluster is inside and how far away it is from its neighbors. A score of 1.0 is literally the holy grail here. It means you've got a perfectly separated, beautiful geometric cluster. A score near 0, that means your boundaries are overlapping and kind of messy. And a -1 means the data point was probably assigned to the wrong shape entirely.
Once we've mathematically proven our shapes are sharp, we have to connect the math back to reality. We do this through cluster profiling. Our algorithm might just spit out cluster 1, 2, and 3. But when we look at the actual data inside those shapes, a real story emerges. Cluster 1 turns out to be high income with wild variations in wine spending. Cluster 2 is low income, low spending. Cluster 3 is right in the middle. Suddenly, our abstract visual geometry has translated directly into highly actionable marketing segments for our retail business.
Part 5. Visualizing with t-SNE. Flattening high-dimensional space. Plotting income versus wine spending on a 2D graph is super easy. But what happens if we add 50 features? Income, wine spending, recency of visits, age, geographic location. Humans hit a hard biological limit. We just cannot visually perceive 50 dimensions. That brings us to a core philosophy of dimensionality reduction. If two observations are mathematically close in a 50-dimensional space, they absolutely must remain close when we squish them down onto a flat 2D screen. To pull this off, we use our ultimate translation tool, t-SNE.
t-SNE stands for T-Distributed Stochastic Neighbor Embedding, and instead of drawing rigid straight lines, it uses nonlinear probability. Think of it kind of like casting a shadow from a complex 50-dimensional object onto a flat wall. The algorithm iteratively shifts and tweaks that flat shadow until the dense neighborhoods in the 2D version properly represent the dense neighborhoods of the original massive object. It's essentially minimizing the divergence between those two spaces.
But to cast that shadow accurately, we have to actively control the process. t-SNE has a setting called perplexity, and it basically acts as a focus knob for our visual lens. It controls how many neighboring points the algorithm pays attention to at once. If you set it to 5, the data looks completely different than if you set it to 100. We really have to tune this knob carefully, balancing the local clusters against the global structure, so we don't accidentally trick our own eyes into seeing patterns that aren't actually there.
And that actually leads to a really critical warning. Never, ever try to read a t-SNE axis like a normal graph. The x and y axis no longer mean income or age. Those original business concepts have been completely dissolved. t-SNE is purely a visual tool for exploring relative spatial structure. It's just showing us who lives in whose neighborhood, nothing more.
So, we've taken messy, unlabeled data, standardized its geometry, mathematically locked it into optimized shapes using k-means, and successfully flattened 50-dimensional objects into 2D shadows that we can actually look at and understand. But it leaves us with a pretty fascinating question. As these algorithms mathematically uncover hidden structures across hundreds of dimensions, what invisible, undeniable patterns might they be revealing right now about our own everyday behaviors? Definitely something to think about. Thanks for joining me on this explainer.